Okay, so if you remember last week, we were starting to discuss induction, that we were discussing the electric field created by a changing magnetic field. Now we will review that. I mean, if you remember the last example we were discussing was the electric field created in a solenoid. Now we will review that, but before that, do you have any questions? Any questions before we start? Well, we were just passing time until we start the lecture. We will come back to that. Any other questions? Now, you were quite opposing the idea that the changing magnetic field should create an electric field. Now, let's just forget that for the time being. What do we know about the nature in general? Okay, one thing we know is that nature should be independent of reference frame. Now, this doesn't mean that everything should be independent of reference frame. There are certain quantities which do depend on reference, which reference frame you are using, like the velocity of an object depends on your reference frame. The position of an object depends on your reference frame. The work done on an object depends on your reference frame, but the acceleration doesn't depend on the reference frame. And hence, the force should be independent of the reference frame. Now we discussed about the Lenz's law, not the Lorentz force, sorry. The Lorentz force, it told us what was the force acting on a charged object. It was the charge of the object multiplied with the electric field plus its velocity times the magnetic field. Now if you remember when we first wrote down this force, there was some hint on some possible problems with this force law. You see, here we have an object that depends on our reference frame, this V, but the F should be independent of the reference frame. If F is independent of the reference frame and V depends on our reference frame, this basically tells us that the electric and magnetic fields that we observe in a given reference frame should also be dependent on which reference frame that we look at it. So if we observe some electric field and some magnetic field in a given reference frame, in a different reference frame, we should observe a different electric field, a different magnetic field, and also a different velocity, so that all of this combination should have the same value independent of which reference frame you are at. Well, basically these two things. And if we want these two things to give a consistent picture of nature, then one thing is, okay, the electric and magnetic fields, they depend on the reference frame. But remember, the charges, the number of charges is kind of independent of the reference frame. If you have a point charge over here in one reference frame, you will have the same point charge there in the other reference frame. It will not change. It will be the same. If the electric field is only created by a reference frame, only created by point charges, then electric field wouldn't depend on our reference frame of choice. There's a single point, and that point charge is the same in every reference frame, so the electric field that would create would have been the same in every reference frame. But it shouldn't be so. So this kind of tells us that there should be something else. And we had this example. We had this in one reference frame. This is what we had. We had a uniform magnetic field. We were assuming that there were no electric fields in this reference frame. And we were moving a rod. This was what we observed in one reference frame. And using our knowledge about nature, in this reference frame, we see that, okay, as this conductor is moving in that direction, in which direction will the negative charges will be pushed? Negative charges will be pushed downward. V cross P is upward. Since it's negative charges will be pushed in the opposite direction. So the electrons will move downward. So this will be negatively charged, and this will be positively charged as the rod is moving. Now, this observation that there are more negative charges on the bottom of the rod and more positive charges on the up part of the rod, it should be the same in every reference frame. If you have some negative charge over here in one reference frame, in another reference frame, it will also be there. Now, let's look at this from a different reference frame. We started to move with the rod itself. That's a change of reference frame. Now, in this reference frame, the magnetic field lines themselves are moving with a velocity. If this is V, these are minus V. And our rod is at rest. And we should still observe the same thing. In this new reference frame, we should still have negative charges on the bottom and positive charges on the above end. Now let me add one more here. Physics is local. Local just means, well, in Turkish it's yerel. It only means that I should be influenced by only the things that are in my near vicinity. I shouldn't be influenced directly by things that are over there. For example, I see you. Well, that's an influence from you on me, but I don't directly see you. What I see is there is light reflecting from you, and when that light arrives at my point, my position, that is when I see you. That is when I am influenced by you. I'm not directly influenced by you. I don't see you directly. So what happens at a given point should be determined by the things at that point, not at somewhere else. Yes, questions? In fact, that is why we created since we want the physics to be local, that is why we invented the concept of the fields. If I am a charge and you are a charge, we always say that, okay, opposite charges repel each other, same charge, opposite charges attract each other, same charges repel each other. You are not attracting or repelling me. You are creating an electric field, and it just propagates outward, just like the light. When the electric field that you created reaches me as another charge, I feel a force due to that electric field at my point. No. You are not touching him. Yeah, that's what we are looking at the fundamental point of view. Of course, the description that, okay, opposite charges attract each other, it works. That's what we observe in the macroscopic world. But what is really happening is I am only influenced by the electric field at my point, which is created by you. But there's still one thing that we didn't explain. If everything is local, how do you create an electric field that arrives at me? That is the question that we need to answer in a couple of weeks. Yes, but you are influenced by the gravitational field created by the quasar, whose position, by the quasar at the point that the quasar was 4 billion years ago, not by its current position. Physics is local. Everything should take time to propagate. Now, why would that be important? Now, if you come back over here, here we have a local picture. At every point we say that there is a magnetic field, and as the electrons in this rod are moving in this magnetic field, they will feel a force created by the magnetic field at their position. Now, at this point, you can say, okay, so in this new reference frame, maybe there are some new charges somewhere over there that we don't see. But I don't care. I want a local description. So how come this becomes this one in this new reference frame? Now, in this new reference frame, in this frame, it was kind of easy to understand. We had moving charges, we had a magnetic field, so there was a magnetic force acting on these moving charges. But in this new reference frame, the charges are not moving, the charges are at rest. And there's a force acting on them. And remember the Lorentz force. The force is equal to Q E plus V cross B. The charges on this rod in this new reference frame, they are at rest. So V is definitely 0. I don't know about B, but there's one thing that I can definitely say. There is an electric field at the position of the electrons. Now, what will create that electric field at that point? Well, the only thing, the difference between this one and this one is here I have moving magnetic field lines. So there's a changing magnetic field. So that is what is creating the electric field over here. In fact, we can even write down the magnitude of the magnetic field. What is the magnitude of the force of, we can determine the charge of the direction of the electric field and the magnitude of the electric field in this reference frame. Now, what is the force acting on that single electron over here, the magnitude of the force? Is EVB. So it should be over here. This is E times the electric field in this reference frame, which should be equal to EVB, because the acceleration in both reference frames should be the same. So this already tells me that the electric field should have this magnitude in this reference frame. And furthermore, the direction of the electric field here, what should be? You see, the electrons are being pushed downward. So the electric field should be pointing upward. This is the direction of the electric field lines. Now, of course, in this case, we could determine the electric field by just switching reference frames. That's not what we would like to do. We would like to give a description of nature consistent in a single reference frame. And our Faraday's law, this is the minus d phi b by dt. Now first we derive this using this moving rod example, but this is valid in general. For any closed loop, if you imagine any closed loop, there will be, if there is a magnetic field in that region, there will be a magnetic flux going through that loop. And if that magnetic flux is changing, it might be changing due to two different reasons. Either you can have, the loop might be changing its shape. In the example of the moving rod, that was what was happening. The loop was changing its shape. Or it might be that the magnetic field is changing. In both of those cases, the EMF generated by going around that loop is given by minus the rate of change of the magnetic flux. Now, if the loop is constant, if circuit or loop is constant, then this EMF will be nothing but E dot dl around the loop. So this law just becomes E dot dl around the loop. This is equal to minus d phi b by dt. So now we have a second source of electric field. Now before we had, if you remember the Gauss law, we had this law, E dot ds integrated over a closed surface. This was equal to Q enclosed divided by epsilon 0. So if we are looking at stationary systems, nothing is changing in time, E dot ds, only the point charges can create an electric field. But now if we have a time-dependent magnetic fields, in that case we also have another source of the electric field. Now, any questions up to here? In this one, I wouldn't do that. Well, there's already a double integral over here if you want. It doesn't depend on time. Now, if there's no time dependence in anything, that's we are in statics, then this derivative will be 0. E dot dl will be just 0. If the loop isn't changing, it's not moving. So you just imagine a mathematical loop that's not changing in time. If you integrate the electric field around that loop, it will be equal to this expression over here. Now, by the way, now we have a problem. Now, if you remember our definition of the potential, now we could define the concept of an electric potential because E dot dl was equal to 0. We had spent like 2 hours proving that E dot dl in electrostatics is 0. Now we have E dot dl is non-zero. But if it is not 0, we cannot define an electric potential. It just doesn't exist. True. In electrodynamics, well, we will be able to define an electric potential, but it will have a different meaning. We cannot define a potential energy in the sense that we define in electrostatics. Yes. The magnetic field is changing. We are just, just like, for example, here we just imagine the mathematical closed surface which wasn't changing in time. Here we are just assuming a loop, mathematical loop, which is not changing in time. No, not necessarily. Now, what this law tells me that, let us assume that in a region of space, I have some magnetic field. Well, what is creating that magnetic field? Well, I don't really care. There's some region of space where there is a magnetic field. If that magnetic field is changing, of course the magnetic field will be created by some other moving charges, some other current somewhere else. If that magnetic field is changing in that region, which can even be vacuum, it doesn't need to be a conductor, it's a vacuum. In that, if magnetic field is changing, there will be an electric field over there. And if there are charges in that region, they will feel this electric field. They will be accelerating, they will be gaining energy or losing energy, etc. Whatever an electric field does, it will do to these charges. How can? Potential difference? What do you mean by potential difference? This is no longer the potential difference. We cannot define a potential. Because the definition of our electrostatic potential was based on the fact that E dot dl was equal to 0. In electrostatics, this is 0. Only in that case we could define an electrostatic potential. Now, since this is not 0, we cannot define it. Now, we can still define it, but it will have a different meaning. It will not be the electrostatic potential. We cannot define a potential energy. You can. But we still need one more thing before that. Look up Tesla coil. Here it's proven. As long as this is not 0, you see the problem over here is if this loop integral is not 0, That means the integral between 2 points will depend on how you go from between those 2 points. So if the integral depends on the path, you cannot talk about potential differences between those 2 points, because the work, if you would like to define it as the work that you do as you go from one point, take a unit charge from one point to the other point, the work that you will have to do will depend on how you go from point 1 to point 2. So you cannot define a work that should be done per charge in the general sense for an arbitrary path. Here. Well, that's just the law. The law of nature. I mean, why do we have F is equal to ma? It just seems that the nature seems to be working that way. Now, the problem here is, another thing over here is, if you want to define a flux, you have to choose an area. You can talk about the flux going through an area. Now, the edge of a closed area is your loop. It's a closed loop. Now, if you don't take a closed loop, then which flux are you talking about? There's no area. Now, we will have to modify the Kirchhoff's law. You see, in Kirchhoff's law, what we did was we just imagined the loop, we calculated the potential changes as we go around the loop, and we equated it to 0. Now, we have to modify it so that when we sum up the potential changes, it will not be 0, it will be equal to some known quantity. Now, we will discuss it, don't worry. Now, let me just mention you slightly. Suppose you take some arbitrary circuit. Okay. So you just calculate all the potential drops. Now the flux, you don't need to have an external magnetic field even. Just because there are these wires going around, there will be some flux going through your circuit around this loop, inside this loop. Now that flux will be some factor times your current. The higher your current is, the higher the flux will be. So it will be, the phi b is proportional to your current, and that proportionality constant, let's just name it L. Now this is your new Kirchhoff's law. It's not, the sum of the potential drops will not be 0, but it will be equal to this factor over here. Now we will discuss this in more detail next week, probably. But we know how to modify the Kirchhoff's law. Now we can ask. Yes. This is how we define a non-conservative force. So the electric force here is non-conservative. Why? Energy is still conserved. Any other questions on this one? I mean, we will come back to this after we discuss the electric field in a solenoid. We will have a concrete example over there. Now, any other questions on these ones? Okay, now, we already have studied one system in which we could create a uniform magnetic field, and that was a solenoid. Now let's just imagine we have a solenoid. So there is this is the solenoid. I'm just looking at it straight from the top. Let's say the current is running in this direction. What will be the direction of the magnetic field? Inside the screen. And what will be the magnitude of the magnetic field, if you remember? N being the number of turns per unit length. This will be the magnetic field we have in the solenoid. Now let's assume that I is changing in time. Now if I is changing in time, then that means the magnetic field inside will be changing in time. Now if the magnetic field inside is changing in time, that would mean that we will have an electric field generated. Now we can use this Faraday's law. A dot dl is equal to minus d phi b by dt. But of course, if we want to use this one, we first have to choose a suitable closed loop, and such that we will be able to evaluate this integral. That is the critical thing. I mean, if you remember the Gauss law, we first analyzed the electric field, and from that analysis we determined a closed surface over which we could evaluate this E dot ds integral. Now we have to do a similar thing over here. We have to analyze the general properties of the electric field, and once we determine that, we could choose a suitable loop over which we can evaluate this integral, although we don't know the electric field. So what do you expect the direction of the electric field to be? Okay, let's see. That is one possibility. The electric fields can start from a point and they can just radially go outward, but that means they start from a point. But electric field lines, if they start from a point, it means there is a charge over there. But inside there is no charges. So since there are no charges, electric field lines cannot be radially outward. That's eliminated. Now what else do we know? Now this is just a cylinder, so if you rotate the cylinder, nothing changes. So that should be also true for the electric field line. Nothing should change. And that gives us leaves us with a single choice, that the electric field lines themselves, they should be closed circles. What is the direction of the circles? Well, I don't know. We don't have to know that for the time being. Let's just choose a closed loop. I mean, for the time being, what I know is that the electric field form closed loops, closed circles. So if I choose my loop to be a closed surface, let's say this closed loop, this is my closed loop. Let's just choose this to be the direction of my loop, of my integral. This is not the direction of the electric field yet. This is just the direction of my loop. I will be evaluating this integral going around the loop in this sense. Now let's just say that that vector is theta hat vector. I'm just defining a theta hat vector. dl is dl in the theta hat direction. E is some vector again in the theta hat direction. I don't know whether this E is positive or negative. I don't know that yet. What I know is that electric field forms closed circles. So electric field at any given point is either in the theta hat direction at that point or in the minus theta hat direction at that point. Now let's first evaluate this E dot dl. Now the electric field vector and this dl vector, if we take the scalar product, this is eta times dl, the product of the magnitudes, which is equal to, on this loop, electric field will be constant, So this will be equal to 2 pi r times E. This is my r. Okay, so I could evaluate this integral on the left. I still have one unknown, and that is the thing that I'm trying to calculate. Now let's look at phi b. Now, what is phi b? Well, you see, flux is just magnetic field times the area. My area and my magnetic field lines is perpendicular to my surface, so there's no cosine factors over there. Flux will be just magnetic field times area. Magnetic field is just constant, so this is just mu 0 I n times pi r squared. So I know that my flux going through this area, I know E dot dl around this loop, so I just put them over here. E dot dl is 2 pi r E. This should be equal to minus d by dt mu 0 I n pi r squared, or minus because the only thing that depends on time is the current. I'm changing my current. So if we just do some simplifications, the electric field is minus mu 0 n over 2 di by dt r. Now, one thing is that it changes, the magnitude increases with radius. It's not uniform. Although the magnetic field is uniform, the electric field is not uniform. So if you would just plot the electric field lines, sketch them. So this is our magnetic field. There is zero electric field inside at the center, and it increases as you go outside. So the density of the magnetic field lines as you go out should increase. Now this is more or less how they look like. The density is quite low towards the center. The density increases as you go outside. That's what this radial dependence is. Now, what is the direction of the electric field? Can you read this equation? So this is what we found. What is this is the direction of our loop, this is the direction of theta hat. What is the direction of the electric field? Sorry? Okay, there is one answer. It says negative theta hat direction. Negative theta hat. In the direction of the current or opposite to the direction of the current? Opposite. Opposite. Well, you don't know, by the way. The direction of the current depends on whether the current is increasing or decreasing. If the current is increasing, that is, this derivative is positive, then electric field is in the negative theta hat direction. That is, the electric field lines will be clockwise. If the electric field is decreasing, that is di by dt is negative, then this E is a positive number, and that would mean that the electric field is in the direction of theta hat, or electric field lines will go in the counterclockwise sense. So it depends on the direction of the electric field line depends on whether the current is increasing or decreasing in time. Now, using Lenz's rule, does this make sense? How? Okay. So if the current is increasing, how do you conclude that the electric field is in the opposite direction using Lenz's rule? No, I mean, okay, these are all the mathematics, and we have derived the direction of the electric field. But if you were lazy to do all these derivations and you were only interested in the direction of the electric field, you could have avoided all these mathematics by just using Lenz's law. Using Lenz's law, if you review the Lenz's law, it just says that if there is a changing magnetic field, there will be an induced, in the application of the Lenz's law, first of all, there is a current there. The induced current will be in such a direction as to oppose the effect that created it. That's the statement of the Lenz's law. Now, there's no current over here. So if you want to use the Lenz's law, we should somehow imagine a current, a created current. We cannot create a current in vacuum. There is nothing to move, no charges over there. But we can just imagine, for example, that we put a conducting wire around this loop. We just imagine it. Now, if you put that conducting ring, okay, as the magnetic field is changing over here, let's say the current is increasing, that means the magnetic field is increasing in the direction into the screen. The induced current will try to oppose it. That is, since the current is induced due to an increase in the magnetic field into the screen, the current should create a magnetic field out of the screen. But if the current creates a magnetic field out of the screen, the right-hand rule, it tells me that the current should be in the counterclockwise sense. Is this true? So let's say if I is increasing, okay, we said if I is increasing, according to the Lenz's law, the current should be in the counterclockwise sense, but if we want to create such a current, the electric field should be in the counterclockwise sense, right? So if the current, let's check our result. If the current is increasing, di by dt is positive. There is a minus sign over here, so E is negative. So the electric field is in the minus theta hat direction. That is, if this result is correct, that tells us that the electric field, if I is increasing, is in the clockwise sense. Okay, where are we doing the mistake? What is the mistake that we did? So that's the question. We did some mistake somewhere. We should have done a mistake somewhere. Where is the mistake? Okay, is this true? No, I mean, we are just saying this is I is in that direction. That's the positive I. Is flux a positive or negative? Or doesn't it matter? Well, it should matter if you change the sign of the flux, you are changing the sign of the electric field. So what is the correct sign for the flux? We just wrote it to be positive, but is it true? How should you determine the sign of the flux? Now, whenever you are studying magnetic fields, your right hand should be quite busy. So this is the direction of our loop, right? Take your right hand, curl your fingers are in the direction of the loop. This is the positive flux. Now, magnetic fields are going in this direction. So they contribute a negative flux. So the flux is not equal to this one, it's minus that one. So it is clear why it should be negative. Now, in this equation, you have two important mathematical elements over there. You have the loop and you have the surface. You have to give a direction to the surface. And the direction of the surface and the loop, they should be consistent with each other. If this is the direction of your loop, positive flux is when the magnetic field is pointing somewhere in that direction, going from this side of the area to this side. And negative flux would be if the magnetic field line is going from this side of the area to the other side. So here we have, since the magnetic field is moving towards the negative side of our area, the flux is negative. If the flux is negative, here we have a minus sign, this is plus, this is plus. So our electric field line, if the current is increasing, our E is positive. If the current is decreasing, E is negative. So if the current is increasing, electric field is in the counterclockwise sense, as we have discovered also using the Lenz's law. If the current is decreasing, then the electric field will be in the counterclockwise sense. No. Now you see, this is the definition of the flux. Now this ds vector, well, of course, what we are doing in defining this flux is we take an area, we divide it into very small segments, and then we assign a vector for each one of these very small pieces. You have to choose about their direction. If you take a very small area, you can choose the S to be in this direction, perpendicular, or in the other direction. That's a choice. That's a choice that you can do. It's up to you to choose it. Now the same thing, so this phi b is this integral. The same thing happens for this line integral. So what happens is, if you are going around this line, this circle in this example, but you have two choices. You can either go in the counterclockwise sense or in the clockwise sense. And that will change the sign of this integral. Now the critical thing is that the direction of your loop, when the direction you use when you evaluate this integral, it has to be consistent with the direction of your area element when you are evaluating this flux. These two things have to be consistent with each other. Well, let's see. With these conventions, these choices, let's assume that the current is increasing. Is the flux increasing or decreasing? Decreasing. Now, with these choices, if I is increasing, well, it tells me the magnetic field is increasing in that direction, but the positive flux is when the magnetic field goes in the opposite direction. So with these conventions, with these choices that I made, if I is increasing, the flux is decreasing. But of course, you could have made the opposite choice. You could have said that, okay, I will choose my loop to be in the opposite direction, in the clockwise sense. In that case, the flux will be positive. Now, it's not important which direction you choose. The important thing is that your choices have to be consistent with each other. Okay, let's come back to that example. Is the magnetic field lines moving? I mean, previously we had this description of the electric field created by moving magnetic field lines. What happens here? Is there a motion of magnetic field lines? So let's see. Let's just assume that we are increasing I in this sense, which means the magnetic field is increasing, right? We are increasing I, so magnetic field is increasing. Its magnitude is increasing. Now we are increasing I, so the magnitude of the magnetic field line is increasing. Now, how is the magnitude of the magnetic field lines related with magnetic field? The magnitude of the magnetic field, how is it related to the density of magnetic field lines? No, that's you are defining the density of magnetic field lines. Let's say we just define the density of the magnetic field lines. How is the density of the magnetic field lines and the magnitude of the magnetic field related with each other? They are the same. If the magnetic field line if the magnitude of the magnetic field line is increasing, that means the density of the magnetic field lines should be increasing. So the density here should be increasing. Now the question is, how does the density increase? We have to be creating more magnetic field lines. So we started with such magnetic field lines, let's say. This is the initial density of magnetic field lines. Now, as we increase, we have to compress more magnetic field lines over there. So how do we do that? We have to be somehow pushing these magnetic field lines towards the center, creating, well, because it's the current, remember. It's the current that is creating these magnetic field lines. So new magnetic field lines, they cannot appear out of nowhere. They should start from the currents, from where we have the current. So they start from here, new magnetic field lines, and they will be pushing these magnetic field lines towards the center. And in time, since they have moved inside, now I have more magnetic field lines. The density have increased. The magnitude of the magnetic field increased because the density, they are denser now. Now, also using these arguments, you can determine the direction of the electric field line. Now, how can we do that? Let's just imagine some test charge over here in this reference frame. I have some positive test charge over there. I'm just imagining. Now, there is this magnetic field line which will be moving in that direction. Let's say that we just go to another reference frame in which this magnetic field line over here, this one only, is fixed. But if this one, in that reference frame, if this is fixed, then this point charge will be moving towards the magnetic field line. This is a positive test charge. But if this is moving in towards the magnetic field line, what will be the direction of the force it will feel? It's a positive charge. Okay, in the opposite direction of the current. So this will be the direction of the force that it will feel in that new reference frame in which this magnetic field line is at rest. But in this original reference frame, that just means that there should be an electric field in this direction. Sure, in this reference frame. No, okay, we are using two reference frames. This is the original reference frame in which we are trying to calculate the electric field. Let's say we are trying to find the direction of the electric field. Temporarily, we just move to another reference frame in which this is at rest. But then this positive charge is moving in this direction. It has a velocity in that direction. But that means it's feeling a force in this direction, in that second reference frame. But the force is independent of the reference frame. So if it is feeling a force in that second reference frame, it should be feeling the same force in the initial reference frame. The thing is, this force in this initial reference frame can only be created by an electric field. So in this reference frame, the electric field should be in that direction if I is increasing. So now, this is how there is a motion of the magnetic field lines, even in this example also. Well, let's see. This is one reference frame. In the alternative reference frame, I'm just looking at this part over here. This is moving in this direction, and I have a magnetic field line at rest. And the force in this reference frame will be Q V cross B. V is in that direction, B is into the screen, so the force is in that direction. Questions? In this one here or in the previous example? Now, we first said that, okay, the problem, nothing changes if we rotate the cylinder around its central axis. That was the first observation. It should be the same for the electric field. There were a few possibilities. One is the electric field lines can be just radially outward. But if the electric field lines are just radially outward, that would mean that they start from a point. But the electric field lines can only start from charges. And there's no charges anywhere, except that maybe on the eye, but there's no charges over here. So they cannot start from anywhere. They cannot start from the central axis. The second alternative was just circles. Circles do not change if you rotate them around their centers. So the circle is consistent with the properties of our system. So that is what we said, that the electric field is is tangent to these circles with their centers at the central axis of the cylinder. That is what we said. We still don't know whether it is in the theta hat direction or in the minus theta hat direction. And that the direction, well, what we did was, once we made this identification, we could evaluate this integral around this circle. And we could calculate the flux that goes through this circle, and then we could just use our Faraday's law, which told us that the electric field, E appearing in this definition of the electric field, has to be given by this expression over here. Then the direction of the electric field itself is determined whether dI over dt is positive or negative. Everything else is positive. In the second one? Well, in this one, we just use the independence of the force as we change our reference frame. instead of just staying in the reference frame in which this magnetic field line is moving, we just move to another reference frame in which this magnetic field line is at rest. But in that reference frame, this test charge is moving towards the magnetic field line, and we could determine the direction of the force acting on this test charge. And that gave us the direction of the force to be in that direction. Okay, let's give a break and see you after 10 minutes.